In this video, let's build Lewis structures for an important class of compounds called free radicals. A free radical is defined as a molecule that has got an odd number of valence electrons. Now, if you've got an odd number of valence electrons, what's going to happen is that it's going to become impossible for you to satisfy the octet rule for all of the atoms in your structure. There is going to be something that is unhappy, and it's going to either donate an electron or grab an electron from another molecule. In other words, if you've got a free radical, it's going to be a very reactive molecule. And this tends to make free radicals very dangerous. They've been implicated in all kinds of disease processes, things like ischemic stroke and cardiac disease. They cause chain reactions that can cascade through the body. There's a whole branch of biology now called free radical biology that studies the role of these types of molecules in biological processes. So what we're doing here is a foundation for that. Now let's start out by doing a structure for a very simple free radical. Let's do the OH radical. So here's our recipe for doing Lewis structures. And we're going to follow that in order every time. We've got an OH. This forms in the upper atmosphere, OH radicals. And let's take a look at how to draw the skeleton structure. Well, we don't have too much choice, right? We only have two atoms. So you can draw the skeleton structure like this. What should go in the center? Well, hydrogen is at the edge of the table. Hydrogen is always going to go on the outside of a structure. You will never put hydrogen as a central atom. So oxygen must be what we're calling the central atom here. So that's step one here. Step two, count the valence electrons. Okay, well, if I look at the periodic table, oxygen has got 6, and hydrogen has got 1 valence electron. So my count of the valence electrons is 7. Now, whenever I get an odd number for this, step 2 here, for the count of valence electrons, I'm always going to pause if I get an odd number of electrons, because then it's going to be impossible for me to draw a structure where everything satisfies the octet rule. And the first thing I'm going to think is, did I do something wrong? Did I add up the electrons incorrectly? Did I maybe forget a sign or something like that somewhere? But in this case, I did everything correctly. There's nothing wrong with my count there, so I can go on. But be aware that when you get an odd number of electrons, very often that's because you've miscounted the valence electrons. Not in this case. Okay, step 3, connect the structure. So let's do that. I've got my OH skeleton structure, and I'm going to connect it by drawing a line between the central atom and the outside atom. And what that's going to do is take away 2 electrons, and I've got 5 electrons left at this stage. Okay, and then I'm going to try to satisfy the outside atoms. Remember, we were calling the oxygen the inside atom and the hydrogen the outside atom. The hydrogen is already satisfied. So there's nothing really that we need to do for step 4. For step 5, dump the remaining electrons on the central atom. That's the oxygen. I've got 5. So let's dump all 5 onto the oxygen. Now it's important that I be aware that I can't dump more than 8 on an oxygen. We're going to see in a minute in another video, we're going to see that you can dump more than 8 sometimes on large atoms, but never on things that are in the second row here. But it's okay because I have less than 8. Now I took away 5 electrons when I did that. So that's what I've got. Step 6. Or this part of step 5, is the central atom satisfied? Is it? How many electrons does it have? 1, 2, 3, 4, 5, 6, 7 electrons. How many does it want? 8. But usually when it's not satisfied, I'm missing an electron here, I can share lone pairs with the neighboring atoms. But there are no neighboring atoms with lone pairs to share with. So there's no way that I can make this structure any better. I'm stuck with this because I had an odd number of electrons. So this is the final structure for the OH free radical. All right, let's check the formal charges. If we get lower overall formal charges, that will kind of reassure us that this was not a bad structure for us to draw under the circumstances. Okay, well, so remember how I do formal charges. I'm going to take the number of valence electrons that something has, and how many valence electrons does oxygen have on the periodic table? 6. Minus the number of sticks and dots that are around it in the structure. There's 1, 2, 3, 4, 5, 6 sticks and dots. So there's a 0 formal charge on the oxygen. How about the hydrogen? How many valence electrons does a hydrogen atom have on the periodic table? 1. Minus the number of sticks and dots that are around it. Well, there's 1 stick. That's all we've got. So it's 0. So look, the formal charge, step 6 told me the formal charges are pretty low. I mean, 0 is as good as you can get. So this is the structure of the free radical. Now that OH radical is one of the things that forms in living cells when radiation goes through them. It can knock apart a water molecule and leave an OH radical like this behind. And this is a very dangerous molecule to have inside of your cell because it wants to go and grab an electron from something else to get its octet. And if that something else is some genetic material, it's just caused a mutation. It's just caused a defect maybe in a DNA molecule so that it does not replicate correctly. And this can lead to spontaneous generation of cancer. This is how one of the ways radiation can cause cancer. So there are stories like this that you can tell with a lot of these free radicals. Let's do a free radical that is associated with air pollution. This comes out of the tailpipe of your car. Your car is hot enough that it can react nitrogen and oxygen in the atmosphere and make a series of nitrogen-oxygen compounds that eventually give us nitrogen dioxide. Let's do the Lewis structure for nitrogen dioxide here. Step 1, skeleton structure. What do you think should be in the center? Look at your periodic table. If you look at nitrogen, it's closer to the center of the table than the oxygen. So I'll put it in the center of my structure. So there's my skeleton structure. Step 2, tally up the valence electrons. Okay, the oxygen has got 6. The nitrogen has 5. This oxygen has 6. So what have I got? 11 and 6 is 17 electrons. That's an odd number, so I double check it. Did I forget a charge there? I didn't. All right, third step is connect the structure. So I'm going to draw a stick between the central atom and the outside atoms. And that took away how many electrons? Each stick counts for 2. So I took away 4 electrons. All right, I have 13 left. On to step 4. Satisfy the outer atoms. How many more do they want? They've got 2. The oxygen has got 2. How many does it want? It wants to get a total of 8. That's the octet rule. So it needs 6 more. 1, 2, 3, 4, 5, 6. That one's done. 7, 8, 9, 10, 11, 12. That one's done. I got 1 left. Step 5. Dump the remaining electrons on the central atom. Okay, well I've got 1. Here's my structure at step 4. If I take that one electron and dump it there, it looks like I'm done. Now it says, is the central atom satisfied? Is it? No. I've got 2, 3, 4, 5. 5 electrons around the central atom. How many does it want? It would like 8. So it would like some more. What can I do to give it some more? Well, I can share lone pairs with the neighbor. If it's not satisfied, the central atom at this point, I'll look at sharing lone pairs. Now I could share a lone pair from this side, or I could share it from this side. But notice if I'm sharing lone pairs, I'm still not going to be able to bring it up to 8. The closest I'm going to be able to get it is 7. And that's as good as I can do. So let's try that. Let's try it on this side. If I try sharing the lone pairs on this side, I'm going to get a structure that looks like this. Remember from our last video about resonance that we have to do it both ways. I could also have shared on that side. So I will get an alternate structure that looks like this. Both of these structures look kind of the same. That's what I get if I shared there. So I have 2 candidate structures. In order to see what's going on here, I'm going to have to assign formal charges. Let's do it for this bottom one. It's the number of valence electrons the oxygen has, 6, minus the number of sticks and dots. 1, 2, 3, 4, 5, 6, 7 sticks and dots. So that's got a formal charge of -1. How about the nitrogen? It's got 5 valence electrons on the periodic table, minus how many sticks and dots? 1, 2, 3, 4. It's got a +1 formal charge. Now how about this one? It's got 6 on the periodic table. And if I subtract the number of sticks and dots, 1, 2, 3, 4, 5, 6 sticks and dots, it's got a formal charge of 0. All right, well, this is telling me a little story here. The formal charges are -1 here. And that means there's a buildup of electrons, too many electrons on this oxygen. And here, right next to it, there is a deficiency of electrons. This has a +1 formal charge, and this has a -1 formal charge. Now, if I was a B student, I would probably do this. I'd say, okay, well, this is as good as I can do. I will draw square brackets around these and put a double arrow between them. And I could say this is a resonance structure here, because both of these have equivalent formal charges. And if I was grading this on a test and it was worth 5 points, I'd give you 4 out of 5 for doing that. But now here's an A student trick, and it only works with free radicals. For free radicals only, you can sometimes get a better structure by moving 1 electron to eliminate formal charges. Now, which formal charges am I eliminating? Well, I want to eliminate this -1 and this +1, and it kind of tells me what to do. This one has too many, and this one has too few electrons. So what I can do is take an electron off the oxygen and put it on the nitrogen. Let's try that. Now I have an odd number of electrons on the oxygen. And I have a structure that looks like this. Now let's check the formal charges to make sure that that really helped. Okay, the formal charge on this oxygen is going to be 6 valence electrons minus 1, 2, 3, 4, 5, 6 sticks and dots. Look what happened. Now we have a 0 formal charge there. How about this nitrogen? We've got 5 valence electrons on a nitrogen on the periodic table minus 1, 2, 3, 4, 5 sticks and dots. So we have a 0 formal charge on that. How about this oxygen? It's got 6 valence electrons on the periodic table minus 1, 2, 3, 4, 5, 6 sticks and dots. Everything has got a formal charge of 0 here. So this is clearly a superior structure to this one up here. So I've drawn a better structure. This would be a B student structure, and I would actually give you a B if you got that far. This will be an A student structure. Now, notice that I could have done the double bond on the other side. So there'll be a structure that looks like this, with a double bond on the left. And the odd number of electrons on that oxygen there. The formal charges on this one will be the same as this one, so I can't distinguish between these two structures. They're both equally good. Now, remember I said that free radicals are unstable molecules? They are. They usually don't have a very long lifetime in the real world. They'll go and react with something pretty quickly. But remember also something that I said in the last video about resonance. When you have resonance, it makes a molecule especially stable. So what you have here is a free radical, but it has resonance to stabilize it. So this thing can actually persist for some time. And this nitrogen dioxide is a very severe pollutant. It can cause severe lung irritation, eye irritation. It occurs in air pollution, and it's been implicated in causing lung cancer as well. So these free radicals are important, and understanding their structure is the first step in understanding their biological action.